Okay, so the last thing we'll look at, this is really quick from 3.1, has to do with figuring out where a function is increasing or decreasing. And to do that, you have to find the local mins and maxes. So it ties in with that. So if I asked you on this graph to name any interval where the graph is increasing, where would you, and we'll use those letters as like marks. It's increasing from where to where? Yep.
B to C.
Yeah, so we're increasing over the interval from B to C. We don't include the B or the C because right at B or C, it's like flat. It's like you're at the top of the hill. You're not going up or down. So between the B and the C, it's going up. How about where is it decreasing? Yep.
A and B and to C to D.
It's increasing as you go from A to B, and then again from C to D. So how would you figure that out in a graph? Well, you'd do second calc, minimum or maximum, and you'd find those values, and then we would write them down. So let's try it on one that I already have written here. So where is it increasing? We answered that. Where is it decreasing? We answered that. And, oops. Right, so let's do this. This will be our last example in this section. So find the intervals on which this function is increasing and then where it is decreasing. Let's type in x cubed minus 4x. Now remember, when you describe an interval where something is increasing and decreasing, we're focusing on x values because that's the variable that's on the right-hand side. Well, it's the only variable in the problem. So you're focusing on that x value. Okay, so here's our graph. It's actually the same one we had yesterday. I'm going to do second calc maximum, and I'm just going to save it. So I have the maximum value. Let's put that over here. And then let's do the minimum value. And we'll save that one as well. So go left, right, and a guess. Okay, and there's the minimum. All right, so if you're going to split this graph up into like increasing and decreasing, how many sections do you have in this graph? Yep.
2 increasing and 1 decreasing.
Yeah, you really got like 3 different sections. You've got an increasing section from there to there. You've got a decreasing section from there to there. And then you have an increasing section from there to there. So let's start by figuring out the increasing sections. So where is it increasing? Well, so let's start with the black interval. What's the lowest value you could pick and still be in the black interval? Negative infinity, because the further left you go, just the further down you go. And that's going to land on the black interval. So that's the lowest. Now, what's the highest x value you could pick and still stay, well, we'll say just before you leave the black section? If you go any higher than this, now you're going to be in the red. Yep.
Negative 1.154.
Yep. So we'll say it's negative 1.15. That's as high as you can go. You go any further, you're in the red section. Right. Now let's do the green one. What's the lowest value you could pick and still be in the green section? What is it?
Yeah, 1.15.
1.15. What's the highest value you could pick? Positive infinity. Okay. So that's the 2 intervals where you're increasing. Now, tell me where you'd be decreasing. What's
the negative 1.1
1.15 and then the positive 1.15.
Yep. Any number between negative 1.15 and positive 1.15 will land you in the red section, and that's a decreasing.
It's so perfect.
Yeah, it doesn't always come out that way.
Is the reason that we're not including negative 1.15 and 1.15 because they're not going up or down? They're just
Right. When you're at 1.15, think of it as like, if you were climbing that, you're right at the top. Now it's like flat there.
you can't do up or down. It's just you're not including that because you can't go to there.
No, you can go to there, but right there the slope is flat. The slope would be considered 0 at the maximum.
So anything below that would be on the left side increasing or on the right decreasing.
Right.
Okay.
So there's a change in the sign of the slope there. That's what's really happening. You go from a positive slope to a negative slope, and right at the maximum, it's a 0 slope. That's why we don't include it.
Maybe I missed something. Why are we using x values and y? Because we're going up and down.
So when you describe an interval for increasing and decreasing, y would be describing like how high and low it goes, but we're not describing how high and low it goes. We're describing like how far left and right you can pick x values and still land in that section. We want to make sure we always describe increasing and decreasing with the x value. If the problem said something about like the range, well, that's when you want to describe with a y value. But this is more like you're describing the domain of the increasing interval and the domain of the decreasing interval. And domain is always x. Question on that? So that was really it from 3.1. It just ties in finding the local mins and maxes into increasing and decreasing. Okay. So last thing we're going to look at in 3.2, it's kind of broken up into 3 separate things. There's a connection kind of between them though. There's continuity, the intermediate value theorem, and what's called end behavior. So we're going to start out with the idea of continuity. Very simply, the idea of continuity means you can draw a graph without lifting your pencil as you draw it. So like if I draw a parabola, did I lift my pencil when I did that? No. That's because that's a continuous graph. How about if I do this? Did I lift at any point when I drew it? No. It's because it's a continuous graph. Now, what if I do something like that? Did I lift my pencil when I did it that time? Yes, I did. There's a break right there. So that would be what we call a discontinuous graph. Okay, so that's the idea of continuity. You never have to lift your pencil when you're drawing it because it's connected, continuous the whole time. But let's try some other ones. Let's try 1 divided by x minus 3. And you do need to put that in parentheses when you type it in. And I'm going to do zoom 6. Could you trace that graph without ever lifting your pencil? No.
Yeah,
That's a graph that's in 2 separate pieces,
I could.
and they don't connect.
Just gotta hold the paper.
So this piece kind of curves down, and then it continues again up top. That is not a continuous function.
You said that break was called discontinuous?
I'll be more specific with what the break is called, but yeah, it's called a discontinuity. But I'm going to write that down. Okay, here's another one. This is called the integer function. The integer function takes in a number, and then what it does is it rounds down. It doesn't round properly. It rounds a number down. So like 5.8, it rounds down to 5. That's what the integer function does. It just takes any number and rounds it down to the next integer that it can. Unless it's already an integer, like 4, well, when you round that, it's just 4. There's nothing to round down to. Yeah.
Isn't that called flooring?
Yeah, yep, exactly. It's like the floor. It's the biggest integer that you can think of. rounded down. Okay, so like 3.8, biggest integer you can think of would be 3. Okay. So if you go to math and you go to number and you go to 5, you can actually graph this. It's not critical you know how to graph it. I just want you to look at it. And because it rounds, there's no decimals in the answer. So what happens is you either get like an answer of 3 or 4. There's nothing in between. So you get these gaps. Could you draw that without lifting your pencil? No. There's a whole bunch of discontinuities in that graph. You'd have to lift your pencil a bunch of times. Basically, every time you go up an integer, you skip all the decimals in between. That's just how the integer function works. It rounds things off. And then something like this would be a parabola. So that one would be continuous. Those two were not. Because we could trace the graph without lifting our pencil in the last one. I didn't draw the last one, but it would be a U shape. All right, so what does that really mean to be continuous? Well, sometimes we don't talk about being continuous everywhere. We might just talk about something like this. Is the graph continuous just on the red part?
Yes.
Yeah. Is it continuous everywhere?
No. Yeah, no.
No. So when we talk about if it's just continuous in a certain spot, we usually call that spot, it's like an interval, like a section. Right? So the start point and the stop point would have to be labeled. Like we could call this start point A and this B. And the idea is if this graph is continuous just in the section from A to B, then that means it's possible to trace from A to B without lifting your pencil. I'm not saying the entire graph is continuous. I'm just saying the section from A to B in this case. Okay, there's a difference. And they just named this interval. Instead of calling, I color-coded it, so I'm calling it the red interval. They called it interval J. That's the name they gave to that red section. Now, let's say I put point C up here. What if I asked you about the interval from B to C? Is that continuous? No. How about A to C? No. Question on that? So if a section is not continuous, well, the opposite of that we say is discontinuous. So interval from A to C, discontinuous. B to C, discontinuous. A to B, continuous. So those are opposites, continuous and discontinuous. Can't be both. So just like I showed you on the last picture, you may draw a picture and be able to find some section that is continuous, like the red section, it's just a small part of it. And then you might be able to look at other sections that are discontinuous. So let's try that with an actual graph. We're going to graph the interval. We're going to graph 1 over x. And I want to find 2 intervals where it's continuous and 2 where it's discontinuous. And remember, when you describe an interval, you use an x value. Let me just move that so we can see it. You know what? I'll do it right next to it so I don't have to scroll up and down. Let's do continuous first. Can somebody give me an x value that you could start at and an x value you could stop at? And if I go between those two, tracing along the blue, I never lift my pencil. Yep.
-10 and 0.
So okay, we probably don't want to use 0 for x.
Well, 0, but like with the parentheses.
Oh, okay, like not including 0. I got you. Yeah. So you could go from -10 up to 0, not including 0, and you would never lift your pencil while you trace that. What's another section that would be continuous? It can be from any number to any number, as long as you don't lift your pencil when you do it. Yep.
Just the 10 to 0?
Okay, you could do 0 to 10. All right, what else? Besides 0 to 10. What is it?
You do 0 to infinity, positive infinity. It just keeps going on.
Yeah, you could do 0 to positive infinity.
Then you can do the opposite, 0 to negative infinity.
Negative infinity.
Opposite direction.
How about a smaller interval that's continuous?
1 and 2.
Sure, 1 to 2. If you start at 1, that's there. If you go to 2, that's there. And if you trace from 1 to 2, you never lift your pencil. Yep. So all those are what we would call continuous intervals. And it would have been okay to put a bracket on the 1 and 2 here, because you could include the 1 and include the 2. That doesn't really matter. It's just with 0, you got to be careful in this one. You don't want to include a 0. How about an interval that's discontinuous?
-10 to 10.
Sure, you can't go from -10 to 10 without lifting your pencil.
How about -2 to 2?
-2 to 2. Basically,
Jeez.
you can't go from any negative number to any positive number in this graph without lifting your pencil. If you try to pass through 0, that's a problem because the graph doesn't connect. Yep.
Could you do parentheses 0 to 0 as a discontinuous?
Well, in that case, I don't think you'd really have an interval because you're starting at 0, you're stopping at 0, and you're not including 0. So you don't, your interval would be, I don't think you'd have one.
Okay.
Yeah. So you want to make sure that your interval starts at a different number than it stops at to make sure you have a value.
So that goes for like all intervals. You can't do like -10, -10. They have to be different ones.
Yeah, if you write the interval -10 to -10, effectively you're writing nothing. Because you're saying, I want you to start at -10, stop at -10, and you can't include -10. You've really limited me here to nothing. So this -10 to 10 is kind of like writing an interval that doesn't exist. It's
So would that count as like I put that on the test answer?
no.
Okay.
What if you did include -10? Like, would that be an interval if you had from -10 to -10?
If you include it,
Yeah, on both sides.
well, if you include -10 to 10 on both sides, effectively now you're describing a single point. So
Does that count?
that would be an interval.
Oh, okay.
Because now you're saying it's every number from -10 to -10, including -10. So effectively, it's just the number -10. So it's like a single dot. Yeah. So I guess technically that would be okay.
Are intervals considered sets?
Intervals.
Are they considered a set?
So a set is usually a finite amount of items. Like you could have 5 items in a set, 10 items in a set. An interval has an infinite amount of items in it. Like if you go from 0 to 5, somebody might say, well, that's not infinite. It's just 0, 1, 2, 3, 4, 5. But it's 3.2, 3.6, 3.9, 4.715. So there's infinite numbers in an interval.
Aren't sets like anything can go into a set, not just numbers?
Yeah, you could have a set of letters. You could have a set of words,
So
names.
can you do like a set of all sets? Would that be infinite?
Oh my god.
A set of sets?
Yeah, a set of all existing sets.
Are you trying?
I know exactly what you're doing right now.
I know exactly what you're
Did we all watch the same
We
video?
all
Yes,
watched the
we
same
did.
video.
We all watched the same video.
So a set of sets, I guess if one of the sets was infinite, then it would be infinite. But if like I did a set, like let's say I had all the first names in the set in this class and then all the last names, and I put those sets together, that would be infinite because there's only so many first names and so many last names to put together. But if I had an infinite amount of things in a set, yes, but usually the way we describe sets in this class is just to use it for a finite amount of items in a set, not an infinite. But yes, I guess you could have an infinite amount, just something we don't do. So there's different ways that you can have a graph that is discontinuous. One way is that you end up with a graph that if you try to plug a certain number in, it would cause you to divide by 0. Okay? Dividing by 0 always causes a discontinuity in your graph. Always. And you saw what it looked like earlier. It looks kind of like that. The two pieces of the graph don't connect. Another way you can have a discontinuity is not an undefined value, but what's called a break. And a break kind of had these, looked like steps. It's not that there's a certain number I can't plug in for x. Like here, there is a certain number you can't plug in. You can't plug in what in the top one? You can't plug in 0. In this one, you can plug in anything you want. All this does is take a number and round it down. You can round any number down. Positives, negatives, fractions, or decimals. But what causes the breaks is the rounding itself. When you round to an integer, you might round a number to 3, you might round it to 4. You'd never round to 3.5 when you're rounding to an integer. That's why there's gaps, because you're only going to integers. Okay, so you can have a value you're not allowed to plug in. You can have something that because of the rounding, you get breaks in the graph. Or, this one is kind of related to the first one. It's a value you can't plug in for x. Does anybody see what you can't fill in for x here? You can't fill in -2. But what's going to happen when you graph that, you're not going to be able to tell that the graph is discontinuous. It's going to look continuous. So it's very obvious when you graph the first one, it's discontinuous. I mean, the two parts of the graph here, they're not even close to touching. Let's graph that bottom. Okay, in parentheses. So if you type in x squared plus 3x plus 2, and then you divide by x plus 2. I'm going to hit graph, and everybody agrees you can't fill in -2, right? Okay. So watch what happens as you get close to -2. Doesn't look like anything happened. It looks like it just drew right through it. I can tell that there's a problem though, because if I press trace and I type in -2, it doesn't give me an answer for y. It leaves it blank. Where if you type in any other number, it gives you an answer for y. You can type in any other number you want. You can even type in something really close to -2, like -1.99999, and it gives me an answer. It's just when you type in -2, you get nothing. So that's called a hole. And a hole in a graph, you can't see it because it's very small. Right? You can plug in numbers up to -1.9999999, that's fine. You can plug in -2.000001. It's probably going to round that to -2 when it shows it on the screen. But remember, it's really not -2. The only value you can't plug in is exactly at -2. So when you draw something like this, if you really want to show that there is a hole in the graph, okay, the way you should draw it is put a circle on -2, like that. That's how you show there's a hole in the graph. So you can draw your line, but you'd never know there's a hole by looking at it. The only way you'd know is by going back to the original problem. So let me show you when you get a hole. So let's take the top and let's factor. How does x squared plus 3x plus 2 factor? Yep.
X plus 1 times x plus 2.
X plus 1 times x plus 2. And what do you notice when you look at that fraction? What's in the top and what's in the bottom? Yeah?
There's 2x plus 2.
Right. They have what's called a common factor. If you have a common factor, it's like they cancel out. And basically, that graph that we just drew is going to look exactly like the graph of x plus 1. You can watch it if I graph it on top of it. The only difference between the two graphs is our graph has a hole in it. The graph of x plus 1 doesn't.
Canceling it out gives you a 0.
Well, canceling, so what you do is when you look for common factors, if they cancel out, because you have common factors, that's when you get a hole in your graph. Now, if you mess the top up, so let's say it doesn't factor now. Let's change it to x squared plus 3x plus 3. Now the top doesn't factor as x plus 1, x plus 2. It doesn't factor nicely at all. So when you graph it this time, there's not going to be a factor to cancel. So this, it's going to look a lot more obvious now that there's a discontinuity. And just by changing that one number, we messed up the factoring in the numerator. And that's much, much easier to see that it's discontinuous. Okay, so when you're checking for a hole, you have to be able to factor the problem and look for a common factor. If there is one, that's where the hole is. Yeah.
Should there be multiple holes?
Yes. Yeah. Like if you were to graph something like this on the calculator, I'm not going to do it all out. If you were to type that in on the calculator, you get a hole at -1 and a hole at -6. And effectively, they would cancel, and it would look exactly like the graph of y equals x plus 3. The only difference is our graph has 2 holes in it, so you'd have to do something like this, where x plus 3 would just be the continuous line. Okay? So 1 and 3 are both undefined values. The difference is how visible they are. 1 you can see easily, 3 you can't see at all. The only way you know it's there is to factor the original part. Question on that?
Can you scroll up a little bit?
So the graphing calculator helps a lot with figuring out if something's continuous because you can see a picture of it and visualize it. So we talked at 3.1, we talked about polynomials. And does anyone remember what we said about the domain? And I said it's always the same. Yeah?
It's always all real numbers.
The domain was always all real numbers. Well, this kind of connects to this idea. But if you take a polynomial and you draw it, you'll never have to lift your pencil when you draw a polynomial. Ever. Any polynomial. So a polynomial could be y equals mx plus b, could be linear. Polynomials can be quadratic. What was the next step up from quadratic? Cubic. I didn't lift my pencil to draw any one of those separately. Quartic, that's one that maybe has like a W shape to it. I think I might have looked at one of those yesterday.
Yeah.
But any polynomial, you can put your pencil down and you can draw it without ever lifting it. And when I say you can draw it without lifting it, I mean you can start anywhere. You can stop anywhere, and you'll never have to lift it. Whether you start here and stop here, start there and stop there, start, stop, it doesn't matter. On a polynomial, you can pick any start point, any stop point, and you'll never have to lift your pencil between the start and the stop. And that's called a continuous function. So a continuous function isn't just a function that has maybe a small section that's connected. The entire thing is connected everywhere forever. Right? You can't find a section on a polynomial that is discontinuous. That's impossible. You cannot find a break or a gap in any polynomial function ever, because they are always continuous functions.
So, I mean, you're always going from left to right. It doesn't matter if you go right to left, right? Or is there a reason why you shouldn't do that?
No, you can go anywhere. We usually, when we just name an interval, we usually specify low value, comma, high value. So that's the only reason I go left to right, because we go low to high. I should write min to max. Yep. Okay, so any question on the idea that polynomial functions are connected everywhere? Yeah.
Just the parent function or all polynomial functions?
All of them. Every polynomial you can possibly think of. So like here's the parent function for a parabola. Well, I can do a vertical stretch by a factor of 2 and that, or a factor of 4, and that's still connected. Every possible parabola you can think of is connected. Skinny ones, wide ones, tall ones, short ones, they're all of them. They're all connected. So last thing we're going to look at is what's called end behavior. I told you the title of the section was continuity, which we just did, intermediate value, and end behavior. We're just going to focus on two of them, continuity and end behavior. So the idea of end behavior is that it describes the behavior of a function on the left and the right side of it. It doesn't describe what's happening in the middle. Here's an example. So maybe that's a, how many turns? 1, 2, 3, 4. I took 5 turns there. So that could be a 6th degree polynomial. You could have 5 turns. The end behavior of this polynomial is up on the left, up on the right. That's what we mean when we describe the end behavior. Compared to something like this, that's up on the left, down on the right. So when we talk about the end behavior, we're really describing what's happening on the left side of it and on the right side of it. Okay, so let's graph y equals x cubed. So the parent function for cubics.
Wait, what are we typing?
Just y equals x cubed. What's happening on the left side of the graph? Which way is the graph heading?
Down.
Down. Which way is it heading on the right side?
Oh.
Up. So the way we would describe, or one way to describe the end behavior, is you can use arrows. This arrow describes what's happening on the left. That arrow describes what's happening on the right. How many different types of end behavior do you think you can have?
2.
4. You could have a down, up, an up, down, up, up, down, down.
Oh, I thought you meant like, is it gonna go up or down? I'm like, what are the other two?
Oh, you mean like for one of the arrows? Yeah. So you got 2 choices for that arrow, 2 choices for that arrow, putting it all together, total of 4 choices.
Yeah.
That makes sense.
Now, the other way we can describe, instead of writing it as an arrow, we might see the same thing written as what's called a limit. So I'm going to read that to you exactly the way it's pronounced, and then I'll explain it a little simpler. So this is pronounced the limit of f of x as x approaches infinity. Okay, what does that really mean? What's happening to y as you head further and further to the right? So let's think about it. Look at this graph. What's happening to the y value as you head further and further to the right? It's going up, and what is it getting close to? It's getting close to positive infinity. So what I just wrote right here, if you describe it as an arrow, is that arrow right there. As you head further and further to the right, what is happening? F of x is just another name for y. What's happening to y as x goes further to the right? This one is saying what happens to the y value as x approaches negative infinity. Negative infinity is on the left.
Yeah.
So what happens to y as you head further and further left? So what happens to y in that graph as you head further left?
Goes down.
And what does it go down to? Negative infinity. Yep. So this, as an arrow, is how you say it in words. The right side is a little bit more formal notation. The left side,
Yeah, I prefer that. I hate doing that other stuff. I hate doing that.
you hate the arrows?
No, I
You,
don't.
yeah, you like the limits?
No, I
That's
don't.
good. I'm glad you do. Okay. So there are 4 types of end behaviors. And actually, let me just put up the chart of them. So rather than writing this 4 types of end behaviors, it's easier to just write the chart because that covers the same thing. There's an easy way to figure out what the end behavior is going to be. And it depends on, well, 2 things. It depends on an exponent and whether it's even or odd. And it also depends on the number in front of that term, whether it's a positive or a negative number. So this term right here, this term would be what we call the leading term. It's the term that has the highest degree. So, say 4x cubed minus 8x squared plus 6x minus 7. The leading term in that problem, well, you tell me, what would it be? Anyone think they know what the leading term would be there? Yeah? So we don't really have an x in that one, like by itself. We don't have an x. Your choices are negative 7, positive 6x, negative 8x squared, and 4x cubed. Those are the terms.
4x cubed.
4x cubed. Yeah. That's what we would call the leading term. Now, if you look at that, the exponent is what kind of number?
H.
Odd. So the exponent is an odd. And the number in front, is it greater than 0 or less than 0?
Greater.
Okay, greater than 0, odd exponent. That's what the end behavior of this entire thing is going to look like. It's going to go down on the left, and it's going to go up on the right. And you might wonder, well, why don't these other terms make a difference? They're just not big enough to make a difference. Right? Cubing something is way more powerful than squaring it or multiplying it by 6. So imagine you plug in like 10 here for x. If you take 10 and cube it, you get 1,000. And then times 4 is 4,000. Right? That's a pretty big term. If you take and plug 10 here, what's 10 squared? 100 times 8, that's 800. But 800 compared to 4,000, 4,000 is way, way bigger. So the highest degree term is what controls the whole thing. These other terms, well, they'll cause little details. Like maybe it causes like a little twist or a turn somewhere in the middle. But overall, what it's gonna look like, 4x cubed controls exactly what it's going to look like. I'm going to write this over here. This 4x cubed is what we call the end behavior model. So basically, if you took your calculator and you graphed that in y1, and you graph 4x cubed in y2, and you zoom out far enough, they would essentially look the same. Okay, the end behavior model is like a prediction of what it would look like if you zoomed way, way out and you couldn't see all the little details. Kind of like if you look at it like Earth from outer space. You might look at two houses and they look identical because you're zoomed out so far. You can't tell the little details. Okay, so this term is called the end behavior model, which I will abbreviate EBM. Yeah.
What would be an instance where it says in the chart AN is less than 0? What would be an instance for that? So when the K is negative?
Just like now, now the first term is less than 0. So let's look at this one. Don't worry about that. It says f of x equals 2x cubed minus 7x squared minus 8x plus 16. What's the EBM? Or what's the end behavior model, do you think, in example 6? Yeah?
Down up. Like,
so the end behavior is when you describe up and down.
okay.
The model is a formula.
Okay.
So what would be the formula that would predict what f of x is basically going to look like? Yeah?
X cubed.
So that wouldn't be a choice here because you have to pick one of the terms. And x cubed is not a term. 2x cubed. Yes. That's everything is being picked up by that, like the whole wheel. It's going to pick it all up. So the end behavior model in f of x is 2x cubed. Okay? It's just the highest degree term. So I'm not going to do it, but if you end up graphing f of x and the end behavior model, they look exactly the same if you zoom out far enough. You can't even really tell the difference between them. If you're zoomed in a lot, you can. They look very different in the first window. But in the second window, it's like the blue one and the red one draw right on top of each other because you're zoomed out to negative 10,000 to 10,000. Okay, so just to be clear on that, end behavior model is a formula like that. The end behavior itself, that's the direction, up or down.
So for the end behavior model, you just put the leading.
You just, yeah, for the end behavior model, you just put the leading term.
Oh, okay.
End behavior model, that's the leading term. So I need to just adjust a couple questions. Okay, so that's the homework for tonight. I will pause the video and put the list of test topics in it. I'm not going to have time to do that before you leave, but I will put them in while you're at lunch, and then I'll put the video online so you'll know exactly what's on the list.
Thank you.
Yep, you're welcome.